In this video, we're going to look at applying triangle inequality to real-life situations. Just to recapture, the triangle inequality means that given a triangle with three side lengths x, y, z, then the side length x, y, z have to satisfy the following three inequalities. X plus y has to be bigger than z, x plus z has to be bigger than y, and y plus z bigger than x. What these three inequalities mean is that the sum of two side lengths has to be bigger than the third one. Or equivalently, a third length cannot be too large. It has to be less than the sum of the other two. So now we'll look at a few problems where we can use the triangle inequality to solve. First question, where to build a station between two schools so that the sum of walk distance from both schools is the smallest. So let's illustrate a little bit. Let's say a school A is here and school B is here. And we want to build a station between somewhere here, this neighborhood, so that the distance, that's a station, let's call it S. So the distance between A and S and B and S, the sum we want to be as small as possible, where we should build this station S. Other than that, the S is going to be around A and B, there's no other restrictions. And this is going to be the difference between this problem and the next problem, which we'll look at later. For now, there's no limitation where the station can be. To solve this problem, we want AS plus SB plus SB. And I'm going to put a high bar over there to mean the distance between A and S and the distance between B and S, SB, to be as small as possible. That's our goal. As small as possible, where the S should be. From the triangle inequality, we know that AS plus SB is going to be bigger than, if we view this as a triangle, ABS. AS plus SB is going to be bigger than AB due to the triangle inequality, right? The two side length sum is going to be bigger than the third length. And if we build S on this line segment, let's put the S prime or S star here, then AS star plus S star B is going to be A and B. From AS and then SB is the same as from A to B. So the shortest distance or the optimal station should be built along this line segment between A and B. And it does not matter where it is. You can build here, you can build here, or you can build here. It does not matter. It's the sum of AS star and S star B is going to be the same as AB, right? So that's where the optimal station should be if there's no any limitation of where the station can be built. But let's say here we have to build a station along a road. Let's say the road goes like this. The road. And the bus station has to be built along the road. Where the station should be built? Well, that station should be now, with this little limitation, it should be built here. Because we know that on this line segment, any point is going to satisfy the sum of A, S star, and S star B. It will be equal AB, which any points will be optimal. Now, with the limitation has to be on the road, we're going to just take the cross point and we call this as my S star. And that's the solution for problem number 1. Now, problem number 2, we add a bit of constraint. We still have A and B, the 2 schools. But the real life situation is there's a road which is somewhere here. So A and B both are on the one side of this road. Still the same question, where we should build a station on this road, let's say somewhere S. Where are we going to build such a S so that the sum of the walk distance is the smallest? So again, we want AS plus SB to be the smallest. Where to build? So that SA plus SB smallest. Now give yourself some minutes to think about this question. This question is not a simple question. Some students will think that, oh, I'm going to connect A and B and maybe do a perpendicular to the road, and then maybe find the middle point, or maybe this point, or maybe that point, right? Where is the optimum point we should build? Allow yourself some minutes really thinking about this. That would be very, very helpful for the discussion afterwards. Now assume that you have done the thinking. I'm going to just slightly draw this graph slightly different. I'm going to draw the road as this way for you better to view. And A and B are like this. You're just thinking about this and then rotate 90 degrees, okay? And I want to find a somewhere S so that AS plus SB is the smallest. We're going to be using something called a reflection principle. Basically what it means is I'm going to take this one as a symmetric line and I'm going to find a reflection of B along this symmetric line. So by that I mean I'm going to take a perpendicular line and find exactly the same distance as this one and call this as B prime. Okay, so B prime is a reflection point along this line. Let's call this line L, which is the road, right? This is the road. And I'm going to reflect B along this line L, get this B prime, let's call it. So the property here is this thing is the same as this thing, and this is perpendicular. So what does that mean? When I reflect this, then this SB is the same as SB prime. Okay, why? Because that's the reflection point. When it's a reflection point, anything that, given any point there, the distance from that point to the reflection point is the same as this point, okay? Because this is the symmetric line. Everything is symmetric. That means the AS plus SB is going to be the same as AS plus SB prime, right? This SB is the same as SB prime. Now I really want to find a point on this road L such that AS plus SB prime is the smallest. But that's exactly the same problem as the first problem. Remember that when I have a road here, what is the optimum point on this road such that AS star plus S star B is the smallest? Is the cross point. So really what I should do is connect AB prime and that point connecting A to B prime and cross with the root L, this is the optimal point. A different way you can see is my AS plus SB prime is always going to be bigger than AB prime. Actually bigger than or equal to. And this equality happens when I'm actually choosing the S on this line segment of AB prime, which is going to be this point. All right, so this here uses this reflection principle, and by no means this is a simple question if you are seeing it for the first time. So please rewatch this if needed and really understand the point I'm trying to illustrate here.